shit. Not yet.
Oh, we're still online already.
Uh-huh. Okay. You're online already?
Yeah, yeah.
Where am I?
Present in full screen, second one. We also have a meeting tomorrow at 2:30 for the Tiny Dragon. Second meeting already.
Hmm?
Second meeting already.
How was the first one?
I got the data set.
Are we talking on YouTube or not?
Yeah, we are. So for small models, we're good. Yeah, but there are some points tomorrow to clarify.
Right. SKLN use sizing, so let's just see.
Yeah, I think that is what we know, right? For really large models in batch processing, sklearn is fast.
Yes.
Even faster than
But
advanced
is it in the real-time processing? It's in the real-time processing, or do we have to?
We have to check it out.
Yeah.
Anyway, I'm wondering if, like, I mean, the C file has more than 4 gigabytes. Over the weekend, it compiled 2 trees out of 6 or something. So I'm not sure if that is the target level we want to have.
What? Okay, we are still pretty ahead of time.
Anything to announce? No, right? Anything to announce?
Just saying that Wednesday is finance forex.
No. We will put another bonus assignment on Wednesday. The Rams jukebox.
Should I put it here?
Just leave it there. So that means we continue the intro introduction next year. We will have to cut something in the end, I guess. So, yes, should have one more for introduction on 9th of January. Probably like every year we have to cut out multi-core. I think I never listened to that part. Even when I listened to RS, that was kicked out. I think I never got that.
Yeah, we should stay stable for some time.
Hmm?
We should stay stable for some time. Okay, guten Tag. Willkommen zu der Rechnerstrukturvorlesung. Letzte Woche hatte Christian schon über Befehle Schnittstelle schon gesprochen. Gibt es Neues hier? Oder nicht? Hallo? Ein bisschen wenig. Ist es besser? Vielleicht oder nicht? Closer. So, was ist wichtig, ist, dass wir zusammen 32 Register haben in RISC-V und zusätzlich haben wir auch ein Register, sogenannten Programmzähler, PC. So, wir benutzen die 33 Register, um Programme zu schaffen. So, ich sollte noch einmal durchgehen. X0 ist 0, ist immer 0. X1 ist Return Address, X2 ist Stack Pointer, X3 ist Global Pointer. Für diese Vorlesung am wichtigsten sind X0, X1 und X2. X2 und X4 sind für uns nicht wichtig. Dann danach x5 bis x31 sind komische Dinge, die wir heute sprechen sollten. Okay? Wir benutzen die zusammen x1 bis x2 und x5 bis x31, um die Programmprozedur zu sprechen. Okay, dann hat Christian auch letzte Woche über Springen, Jump schon gesprochen. Hier ist eine Schleife, eine While-Schleife. So, while save I is equal to k, dann I ist zum I plus j zugeordnet. Was ist wichtig, ist das immer, wenn wir in Hochprogrammiersprachen gucken, das ist für Schleife ist immer so, wenn Bedingung A erfüllt, dann machen wir etwas. Aber wenn wir mit RISC-V oder Assembly gucken, was benutzen wir, ist immer das. Wir springen, wenn etwas erfüllt oder nicht erfüllt. Es bedeutet, wenn wir hier über gleich wie k dort gesprochen, dann danach, wenn wir springen möchten, dann springen wir mit dieser Bedingung, sodass diese Bedingung nicht erfüllt ist. So, gibt immer diese Negation. So, was sollten wir gucken ist, dann laden wir zuerst ein Konstant. So, diese Konstant 4 ist im Register x10 zugeordnet. Und dann machen wir I mal 4. Dann speichern wir das Ergebnis im Register 9. So, x10 hier ist 4, x19 nennen wir hier ist I. So, I mal 4 speichern wir im Register x9. Okay, dann laden wir die Datei. Das bedeutet, diese Datei in die Adresse von Ceph von Offset x9 ist dann in Registerart zugeordnet. Das bedeutet, nach hier Registerart ist Ceph von I. Okay, dann haben wir schon die Datei von Ceph von Adresse I. Und dann sollten wir Register Xart und Konstant K vergleichen. Wenn die zwei gleich sind, sollten wir weitermachen. Wenn diese nicht gleich sind, sollten wir springen aus. Okay? Wenn wir über Springen gucken, dann sollten wir vergleichen, ob die zwei nicht gleich sind. Das bedeutet, wir machen Branch not equals. Wenn x8 nicht gleich wie x21, dann springen wir zum Exit. Das bedeutet, wenn die zwei nicht gleich sind, dann springen wir aus. Wenn die zwei gleich sind, dann machen wir weiter. Was machen wir weiter? Wenn die zwei gleich sind, dann machen wir I zum I plus J zugeordnet und dann springen wir zurück zum Loop. Okay, dann springen wir dann zurück hier. Okay, das ist für While-Schleife. Dann, Sie sehen schon ein bisschen Befehle. Jump-Label ist ein Sudo-Befehl, der zum benannten Label springt. Load immediate Konstant ist ein Sudo-Befehl, der 32-Bit-Konstanten laden. Als ein Sudo-Befehl kann man vielleicht mit mehreren Befehlen realisieren, zum Beispiel load immediate. Das gibt ein Immediate mit 32 Bit-Konstanten. Dann brauchen wir vielleicht zwei Befehle. Eins Load Upper Immediate und dann Load Logic. Okay? Und dann es gibt auch weitere Befehle, zum Beispiel Branch greater equals to, Branch less than equals less than 0, Branch greater than, Branch less than equals, Branch less than or equal, Branch greater than 0. Okay, das kann man mit diesem Zweigenbefehl erfüllen. Manchmal sind diese Befehle Direktbefehle, aber manchmal sind auch diese Befehle Pseudo-Befehle. Es bedeutet, wir brauchen vielleicht mehrere Befehle, um solche Befehle zu realisieren. Man kann auch, wenn wir über solche Pseudo-Befehle gucken, es kann man mit Set-Befehlen realisieren. Diese Lösung kann man mit Set less than Befehl oder Set greater than Befehl führen. So, was bedeutet ist das? Wir bekommen zusammen drei Register. Set less than RA, RB und RC. Das bedeutet, dieses Register RA ist 1, wenn RB ist less than RC. Das Register RA ist dann nur, wenn RB ist nicht kleiner als Register von AC. Okay? Dann können wir im nächsten Befehl überprüfen, ob A nur oder 1 sind. So, dann können wir dann Branch not equals to 0. Branch not equal to 0. Wo ist das? Kann ich finden. Where is branch not equals to 0? Or branch equals to 0? Don't find it. Do we have that? Branch not equals to 0? Branch equals to 0?
I think it was somewhere.
I don't find it. But there's somewhere. I don't know where it is. In an exam, you will receive the reference set of the instructions. If you cannot find one, what should I do?
Also ich hatte ja schon mal gesagt, in der Klausur gibt es vielleicht RISC-V, vielleicht auch nicht. Also es gibt irgendeine Liste an Befehlen und die halt da stehen, die muss man dann benutzen und mehr gibt es nicht.
The only chance you want to use another instruction is that you believe that we make a mistake. But I'm pretty sure that we don't make mistakes. If so, you will get 3 points. But I don't think we make any such of mistakes anymore. Okay. So use the instructions you get in the reference. And then if there's no branch not equals to 0, don't use that. You have to create that, and we will see. Okay. Good. Yeah. But if you have only 0 or 1, you can also do branch greater than 0. Or branch, if its branch is greater than 0, it's 1. Otherwise, it's 0. Okay? Sorry. Branch less. I don't think I can continue. Okay, sorry, I was wrong with what I just said. So let's go ahead. Okay, so dann, man kann auch Vorschleife gucken. So, hier ist ein anderes Beispiel, Vorschleife. J ist nur zugeordnet. Und dann vor, es gibt 3 Dinge. Zuerst I ist nur zugeordnet. Und dann, wenn I kleiner als N, machen wir diese Schleife weiter und am Ende der Schleife sollten wir I zu I plus 1 weitermachen. Das bedeutet, was machen wir für diese Vorschleife ist das, wir waren zuerst I zum nur zugeordnet, dann vom Anfang der Schleife sollten wir gucken, ob I kleiner als N ist. Es bedeutet, wir springen aus, wenn I größer als oder gleich wie N. So, wir sollten hier mit branch greater than or equal setzen. Okay, so dann laden wir xi Variable j im Register x5, Variable I im Register x6 und dann wir gucken, ob x6 größer oder gleich wie x7. Wenn ja, dann springen wir zum Ende. Wenn nein, dann machen wir weiter. Was wir weiter? Dann setzen wir j zum j plus I. So, dann x5 ist j, x5 ist zum x5 plus x6 zugeordnet. Und nachdem haben wir das Body von Schleife fertig gemacht, dann haben wir am Ende diese j zu j plus 1 zugeordnet. Und dann springen wir zurück zur Schleife. Bekommen wir diese For Loop. Okay? Das war nicht so schwierig zu verstehen. Wir springen aus, wenn dieser Befehl zur Schleife nicht erfüllt. Was sollten wir immer aufpassen, ist, dass wir sollten diese Bedingung negieren. Ja? Wenn wir nicht hier richtig Negation machen, dann haben wir eine Falschbedingung benutzt. Ja? Gut, es gibt auch andere Jump Register. Der Jump Register Befehl. Jump Register mit dem Namen springen wir direkt zu die Adresse von diesem Register. Das bedeutet, Jump Register zum Beispiel x3, dann springen wir direkt in diese Registeradresse. Das bedeutet, wir würden die Programmzeiler direkt zu den Inhalt von diesem Register zugeordnet. So, zum Beispiel, wir haben zurzeit etwas im PC, dann bekommen wir Jump Register x3. Nach diesem Befehl springen wir zum den Inhalt von dem Register x3. Das bedeutet, im nächsten Stufe führen wir zum Register zum Adresse nur aus. So, jetzt können wir zum Beispiel dann mit solchem Konzept am Switch Statement zu realisieren. Hier ist ein Switch Statement. Das bedeutet, wir bekommen ein Integer k. Wenn k nur ist, dann machen wir etwas. Wenn k 1 ist, dann machen wir etwas. Wenn k 2 ist, dann machen wir etwas. Wenn k 3 ist, dann machen wir etwas. Wir haben einen Namen, das k immer zwischen nur und entweder nur 1, 2 oder 3 ist. Okay? Es ist natürlich wichtig, dass wir hier einen Break machen, sodass wir nicht nach anderer Pfad weiterführen. Okay, wie können wir solche Switch-Anweisungen realisieren? Wir können zum Beispiel die Adresse von Case nur Case 1, Case 2 und Case 3 in ein Array schreiben. Dann können wir direkt gucken, ob K nur ist, 1 ist, 2 ist oder 3 ist. Dann nehmen wir direkt die Adresse von einem Array und dann können wir dort direkt springen. Wie können wir diese Adresse springen? Schreiben wir einfach die Zieladresse im Register. Dann rufen wir direkt Jump Register auf. Okay, so es ist so 1. So, das müssen wir so realisieren. Dann es gibt eine Jump-Tabelle. Diese Jump-Tabelle bauen wir einfach die Anfangadresse. Dann setzen wir diese Adresse R0 von hier, dann R1, R2 und R3. Okay? Und dann können wir direkt gucken, ob K nur 1, 2 oder K 1, 2, nur 1, 2 oder 3 ist. Das bedeutet, wir haben eine Tabelle, in jedem Element speichern wir 32-Bit Adresse. Dann, wenn wir die richtige K, wenn wir die richtige K haben, dann können wir diese Adresse im Register zugreifen und dann machen wir Jump Register. Diese Jump-Tabelle müssen wir im Data Segment einsetzen. So, können wir so machen. So, dann nehmen wir an, dass wir diese Jump-Tabelle schon in Data Segment haben. Und dann haben wir R0, R1, R2 und R3 aus dieser Anfangadresse. Dann R0 ist F zu I plus J zugeordnet und dann Break. Break bedeutet, es ist Spring aus. Ja? So, es gibt dann zwei Befehle. So, das ist R0, dann Jump Out und dann R1 ist G plus H, etwas anderes, dann springen, dann R2, Subtraction, dann springen aus, Case 3, dann man springt aus. Ja? Das ist am Ende, man braucht nicht auch springen. Okay, so dann was bauen wir für Switch? Für Switch bauen wir einfach zum ersten die richtige Adresse zu berechnen. So Register 9, dann bekommen wir aus K mal 4. Das ist das Offset von Anfangadresse. Dann laden wir direkt die Adresse, die wird im Jump-Tabelle mit Offset x9 schon gespeichert. So, wenn K nur ist, dann hier x9 ist nur, das ist die Anfangadresse, das ist R nur. Wenn K 1 ist, dann x9 ist 4. Das bedeutet, dann laden wir die Adresse R1 und weiter. Dann was machen wir? Next ist einfach Jump Register zum Register X8. Okay, das bedeutet, wir laden hier, okay, ganz langsam, also X9, glaube ich, ist 2. Dann können wir direkt in L2 weitermachen. Okay, das ist nichts schwierig. Man sollte einfach überlegen. Wenn wir springen mussten, springen wir aus. Deswegen, wenn wir über For Loop oder While Loop realisieren mussten, dann sollten wir die Negation als Bedingung zuschreiben. Und natürlich, man sollte immer in die richtige Adresse springen. Wenn die Bedingung nicht erfüllt ist, dann machen wir PC aus PC plus 4, dann führen wir den nächsten Befehl aus. Okay. Bisher ist die Vorstellung von RISC-V und Instruction Set Architecture. Gibt es Fragen? Zu einfach. Normalerweise bisher. Okay. The next one is going to be a bit complicated. And this is the reason why we talk about instructions. Usually, I would talk about this part 3 times. And usually, it's 2 times today and 1 time in the next lecture. But because the next lecture is in the new year, after the new year, sorry. So I guess let's try to do 2 times. And in these 2 times, I would first use English, and then German, and then English again. Okay. So what we're going to talk next is called stack. You probably know Stack Overflow. The famous website that every engineer has a bookmark on it or multiple bookmarks on it. The stack may have an overflow. And the name of the website is due to the very nice feature that we have in computer systems called stack. And since you know that the stack overflows, so there's a website named after that. So we're going to talk about that. And you may have also get amused by the ChatGPT. How many of you have tried ChatGPT yet already? Okay, so it has been banned by Stack Overflow because of misinformation, of the misusage of programming stuff. So let's try to get something that is correct. Okay, to understand what is stack. So to understand the stack, you have to first understand what we are doing. When we write programs, we need to write something. And then we don't want to just write instructions after instructions. We don't just want to write statements after statements. We want to write something called functions. Okay? And we want to just build a program based on a lot of function calls. In this example, we have a main program. The main program calls function A. In the program function A, program function A calls function B. In the function B, the function calls function C. In the function C, it does whatever arbitrarily. Okay, and then after function C returns its computation, the result is given back to function B. And after function B finishes its computation, the result is given back to function A, and so on and so forth. And after function A finishes, the result is given back to the main function. Okay, so the key part is that when you design a function, you think locally. When you write a function C, most of the time, I'm saying about most of the time, most of the time I only think about what I need to do in the function C. I don't care about others, okay? I take whatever variable I use, I take it, use that, declare it as I. I don't care what I is, I use that forever, do whatever for loop, and in the end I just discard it, okay? Assuming that someone would take care of it. And if I want to declare an array, I just declare an array in my function. And then I say this array has a size of 200. I just use it, at the end, someone takes it back, right? Assuming that someone takes it back. And then, if you need something permanent, you need to new an object in Java, right? You need to do the memory allocation in C, or you need to new an object in C++. Whatever language you use, it follows that structure. Anything local can be arbitrarily used. You take that at hand. And anything that you need to somehow persistent across function calls, you need to either put that into the data segment or put that into the heap. Okay? What I'm saying here is that anything that you can think of disposal, that you take it at hand, you drop it at hand, you don't care about the allocation or delocation, is in this concept of stack. So where's the stack? Stack is a memory area that grows or shrinks according to the function calls. At the beginning of your program, your stack is very small. After you finish the program, after the main function calls function A, the main function puts some of its memory aside and then calls function A. And function A starts to use something local, starts to declare some calculation, and then put something to the registers. And at the moment when function A calls function B, it has to store some data. It has to somehow, then function B will start to use some additional memory. And then the stack somehow grows up. And then after a certain moment, you have finished the function calls. The stack shrinks again. Okay, so let's start with an assumption that the stack starts from somewhere that is specified by the system. It either grows or shrinks. Okay, this works everywhere. And if a stack overflows, what does that mean? That means this. So this is the data segment we can think of. It's the memory architecture we can think of. We have already talked about the text segment. The text segment stores the instructions that are read-only. The data segment stores the initial constants, the global variables, the heap, if you want to call it, over here. And so now we start from this 0 address, and then we have this data segment. The data segment grows, in this case, towards positive address. That means that you start from the base address 10010000, and whenever you do more memory allocation, you get more address towards that. When you new an object, you put it to the data segment or the heap, and it grows towards more positive address. We have limited memory space. So on the other hand, we can also start from a fixed address of a stack and grow in the same direction. But this would end up in a nice partition that your data segment is limited to the scope you have, and the stack segment is limited to the scope you have. Since we don't know how much we need from the data, and we don't know how much we need for the stack, let's do a smart design that the data grows in this direction and stack grows in the opposite direction. So we have this area in total for the stack and data. So the data grows towards positive address. The stack grows towards the negative address. Okay? When these two segments overlap with each other, then anything random could be possible. And this is the moment when you have a stack overflow. If you want to attack something, you make a large buffer size. And if buffer size is more than the stack size you should have, then you store something to the data segment instead of stack, and it's wrong. Okay? And the opposite as well. So you don't want them to overlap. You don't want to just give this to the system that you have zero control with. So you want to, have a good understanding of stack and avoid stack overflow. And as I always said, understanding the behavior of stack is the basic knowledge of a computer scientist. Without knowing how stack works, your programming is at a very brittle state because you don't know what you're actually doing. You think that you are using that variable at hand. You thought that the variable is stored somewhere, but it's stored in stack. You thought that your variable is stored in stack, but it's in a heap. And you thought that this variable would be reinitialized, but it's not because it's in a heap. You thought this would be by default initialized to 0. It's not because it's a stack. It's a value that was already used last time. When you initialize a variable, why do you need to set a variable to 0? It's very simple. Because when we shrink from the stack, we never reinitialize the variable to 0. We don't touch our memory space because there's an assumption when you get the new space for free, you would initialize that. If you don't initialize the variable, it means that you don't care. If you don't care, then no one cares. The computer doesn't reinitialize for you. You have to initialize everything by your own. And if you think that you store that data in the heap, but unfortunately you put it wrong, it's in a stack, next time when you want to use that, it could be updated by someone else. The data you thought that you operated before is not there. You are operating something else. Okay, so understanding the stack gives you a good understanding about what you're actually doing in your memory space. Okay, good. So let's try to understand what we need to do. So we are calling those functions, and let's see, and over the time, your memory somehow increases. So what do we actually need to understand about that? So each function is implemented as a sequence of instructions starting from an address. So when we call function B from function A, then function A needs to do something before calling function B. What does function A have to do? First, the function A has to tell function B where to return from. Sorry, where to return to. So function B could be called by function F or function G. Function B itself doesn't know where to return to. When function A calls function B, function A has to tell function B, dear my friend function B, after you finish your execution, please return to my address. Otherwise, the friend of function B could randomly return to somewhere else. So first thing, you need to set up the return address. Which return address do you need to set? You need to set this return address to the current program counter plus 4. So the function B, after it returns, knows that it has to continue from this next statement. Okay? Now, function A calls function B. And since function B has no clear idea what function A has done, function B would do something arbitrary within each context of function. It changes the registers, assuming that it can use all the registers. Therefore, after function B returns, function A will say, oh my God, what happens to my registers? They are all changed by function B. So function A somehow has to realize that the dear friend function B would use some registers in the scope of function B, so function A would have to store those registers to some memory. Otherwise, function A would have no idea to recover the contents of those registers. This is called What do you store that? You store them in a stack. How many do you need to store them? You need to know how many registers are useful. And then, when function A calls function B, function A, of course, can store all the registers. We have in total 32 registers that store all of them. Now when function B enters this program, if it doesn't know what function A does, function B will say, oh, my dear friend function function A or function F, I have no idea what you have done. Let me restore all the registers for you. So then you get this 2 times copy, and this is what you don't want. So you want to have a protocol that some registers are stored by the caller, in this context function A, some registers are stored by the callee, in this case function B. And this is what we are trying to discuss. Over here, to understand how everything works in stack. So, therefore, what do we need? We need the first instruction, jump and link. So, think about what we want to do. When we call a function, we want to tell that function that please, after you finish the execution, you need to return to the next program counter, the current program counter plus 4. So what do you need is that I need to do 2 things at the same time, or atomically in computer systems. That means that these 2 must be done together. And this is this instruction jump and link. What it does is that it jumps to the target address and link the return address. Jump and link. Is that right? Or jump and link? Okay, yeah. Jump to the, where is the link part? The RD? Where is the target register?
Yes, it's the link PC.
The link PC, where is that?
No, it comes to RD, right?
It comes to RD, but there's no RD here.
No.
Yeah. Okay, good. So, looking for the comment. So, jump and link is to happen at the same time. It was accidentally deleted when we reorganized the slides. So, first, which address do we jump to? We jump to this strange address, which I will explain later. And in fact, this address is the address of the function you want to call. And where do you link? You link the target register, in this case RD. So RD is then set to the program counter plus 4. Okay? So now let's have a look at which address we jump to. We jump to the program counter plus the sign extension of the 20 bits here, added with a 0 at the end. It's a sign extension. So you explain sign extension. That's it, right? Sign extension means that we have potentially plus or minus. And so in this format, jump and link, we have an immediate of 20 bits. That means that we can encode in total 2 to the power 20 different addresses. Yeah? Starting from minus 2 to the power 19 to 2 to the power 19 minus 1. These are the immediates we can encode. And the nice spec of RISC-V decided to do something strange. they wanted to add a 0 at the end. So that means that, okay, one bit at the end is 0. It's always 0. We are in a granularity of 2. So it starts from 2 to power, so minus 2 to power 20. And the next one is minus 2 to power 20 plus 2. The next one is minus 2 to power 20 plus 4, and so on and so forth, to 2 to power 20 minus 2. And why does it add a 0 at the end? It's a political decision. It could add 2, like a MIPS. It could add nothing there. The main reason is that in the scope of RISC-V, you have the possibility to use half a word. That means that the granularity of instruction could be 2 bytes or 4 bytes. If you have granularity of 2 bytes, then your address space would be in a scope of 2. If your granularity is 4, then you have a space of 4. If the granularity is 4, then you would add 2 zeros at the end, like the other RISC instruction sets. The reason to add 1 0 at the end is just because there's no possibility that you have one instruction with only 1 byte. You must have at least 2 bytes in RISC-V. And you can say, wait a second, Professor Chen, you always say 4 bytes. Right? Yes, 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 4 bytes. Yeah. If we talk here about a spec, then I would put another 0 here. But since we said that we are teaching RISC-V, so I would like to not go to be too different from the standards. So let's add 1 0 here. That means that if you have a RISC-V in 16-bit format, you would have 1 0 here. Okay? So having 1 or 2 is only political decision, nothing to do with the understanding. So now we know that. That means that the scope we can jump to is in total 2 to the power 21 megabytes relative to the program counter. If you use jump and link, or if you use jump, because it's the same instruction. Okay, the jump instruction, in fact, in RISC-V, is implemented by using jump and link. Okay. Okay, good. So now let's have a look of what we can do. So X1 is our dear friend for return address. So jump and link. So it means that when we do jump and link, we would put the return address to X1. So now we have this function. So A calls, main function calls function A. And then function A does something, and it goes back to the main function. The main function starts from address 400000, and that's our current program counter. It's 00400000, and then this instruction is jump and link to the address. So now we do this by first putting this to register 1. So what do we do? First, we need to set the return address. But these two happen at the same time. So when I say first and then, that means that happen at the same time. So the return address is the current program counter plus 4, and we store that to X1, the return address. So X1 is program counter plus 4. And then the program counter is set to somewhere, and then they sum up together. It's magically the starting address of function A. So this would be 0, 0, 4, 1, 0, 0, 0, 0. Okay? And now you start to do something here and there, and in this case, I don't do anything. So what I need to do is to go back to the return address. I just jump to the return address. I call jump register x1, and then I'm back to the return address. Okay? Good. So any question for this? It's very simple. First, we call a function. When we call a function, we prepare the return address for the function to come back. Second, at the end of the function, it has to return to its return address. Okay. So now, if you do this with jump and nick, then this address is only limited to 2 megabytes. And if you want to jump beyond that address space, you need another instruction. Another instruction is called jump and link register. So jump and register is almost the same as the previous one. So this is the missing one. So Christian, remember that we have to put this to the other slide. Yeah? So we first set the target register to the parent program counter plus 4. And where do we jump to? We jump to the address specified by the register RS with some offset. So how much can we do in the offset? It depends on the format. The format is jump and link register. It's a format E. And it has 12 bits in the immediate because it has 2 registers and some additional functions. It's similar to load immediate. And in this case, what you do is that you basically put this content that you store in the address plus some constant that you specify in the immediate. We have in total 12 bits here. Let's take all of them and add 1 0 at the end with the same consistency of the granularity of 2 bytes. Okay? And therefore, we could use this to jump to any address we want without any limitation. So let's look at an example. There's a jump and link register. The target, the register to be linked is x1. So let's put it this way. If you use RISC-V, you call jump and link or jump and link register. If you don't do anything strange, at least in this lecture, then your target register is usually x1 or register, return address register. And then what we have here is x2, and the immediate is 0x745. Let's assume that x2 is this number. And then we have 0x745 as our immediate. Then what we get is that we are jumping to this address of Is that correct, Christian? I think we need to change the slides. Because, let me see whether we are doing this right. Oh, this is correct. The next one is right, wrong. Okay, so this one is correct. So 0745, and we need to shift to the left. Okay, so let's put it down. So this is 0, 0, 0, 0, 0, 1, 1, 1, 0, 1, 0, 0. Okay? This is 0x74. Okay? And now we add one more 0 at the end. So there's one more 0 here. Okay, so let's sum them up together. So this is 8. And this is E. So we have to jump to this address. 0x, 0ff, ff, 0 E8.
The next slide is correct, by the way. The next slide is correct.
The next slide is correct. Okay, let's have a look. Okay, so let's have a look over the next one. So now that means that what we can do is that we can first do low upper immediate to load the upper 20 bits to a register, and then use a jump and nick register to find the remaining part of the offset. And why is this correct?
Also natürlich ist es so, dass von der Konstante das letzte Bit abgeschnitten wird. Aber natürlich muss ich das als Programmierer nicht selber ausrechnen, sondern das macht der Assembler für mich.
Ja, das ist richtig.
Also ich schreibe eine Zahl dahin, die durch 2 teilbar ist. Der Assembler teilt die durch 2 und kodiert das im Maschinenbefehl dann in die Konstante, die durch 2 geteilt ist. Aber ich schreibe die richtige Zahl dahin, also das richtige Offset. Das durch 2 teilen macht ja der Assembler.
Verstehe nicht. Warum so?
Sonst müsste ich ja immer rechnen, wenn ich programmiere.
Na, ja, das weiß ich, ja. So, okay, okay. The thing is that what is actually implemented in the assembler, or it's actually implemented in ROS. Yeah, so what we're talking here is that if you do it by hand, you want to call it in an instructions format like this, then you would have to do this shifting manually. Okay? Now, the question is that what is actually encoded for this constant, 0x7474f? If this is encoded as shifted to the right by 1 bit, then everything is fine. If it's not, then it would be encoded to left. And what we would suggest you is never to use any way of this in your programs. In ROS, when you jump to the target address would be encoded accordingly and will be calculated by the compiler to the right address. So you don't make such misalignment of those instructions. Okay? So whether you have a 0 or not 0, at the end, it's basically irrelevant to you. It's only about the format. It's about the implementation of the compilers, and so on and so forth. Does this solve our concerns? Oh, yes. Okay, good.
Just want to check if you get an error if you put a misaligned address.
He wants to try something strange. Let's call it for that. Okay, so now we know how to call the address. We still haven't talked about the stack concept. So now let's do it again. So now since we have this concept that we store something, then we get more, and then we get more, and we get more. So the size of your stack becomes larger and larger, and your stack grows over time, and you would have to handle that accordingly, and it also shrinks over time. So how does this work? So we have this so-called stack pointer, and unfortunately, this is the only thing we have. Of course, if you want to, you look at the modern architectures, you have something called stack frame, but let's do it a bit easier with the stack pointer. What is a stack pointer? We assume that we start from the base address of the stack, the base address. as the ground zero of the stack. And whenever we need more space in the stack, we need to know how large the stack has been grown so far. The stack pointer points to the point that the current stack has been grown to. So when you need to have, for example, 20 bytes for the function A before function A calls function B, then what you need to do is to move the stack pointer 20 bytes less in the address space. And you get 20 bytes more. And after that, if function B needs to call function C, it has to store something in the memory. It starts from the stack pointer and then take, for example, 32 bytes to a lower address. And it gets 32 bytes here to write. And in case function C needs 40 bytes, then it starts from the stack pointer plus 40 bytes, sorry, in this case, minus 40 bytes, and it gets the corresponding address in it, and right there. And after function C returns, lost memory area used by function C will not be needed anymore, so it goes back. So how does function C know where to make the stack less? When function C decided to ask for 40 bytes for its stack place, at the point, function C knows where the stack pointer was. What function C needs to do is to restore the stack pointer to the previous ones, and so on and so forth. At the end, you can go back over here. So register 2 is stack pointer, so then we need to put our register 2 correct. Okay, so what should we do? So let's now make sure that we do it right. We have one register called x1, and x1 must be protected. If x1 is not correctly protected, then we would jump arbitrarily back to some places. Let's do it. So we are in this main function, and then we call function A, and so on and so forth. When we call function A, we would first, before function A calls function B, before function A calls function B, this register x1 must be protected. Because as long as we call jump and link, as long as jump and link is called, the x1 is gone. Then function A would have no home to return to, because there's no x1 anymore. Oh, sorry, there's still x1, but this x1 is not my x1. Okay? So let me repeat this again. When the main function calls function A, it calls jump and link. And after the point of time, we start to run function A, and the register x1 is set to the return address to the main function. And now function A would like to call function B. Before this function is called, the function A needs to make sure that it somehow stores the address it should return to the stack. Because after calling jump and link to jump to function B, the x1 will be replaced. And function A would have no address to return to. To make sure that function A still knows where to return to, function A has to first push the register x1 to the stack. And then after calling the function B returns. Then function A has to restore the register x1 from the stack. Because when function B returns, the value of x1 would be set by function, would be the return address of function B. Okay? So then you have to do this. When you further call function B, the same thing. Before calling function C, x1 has to be stored to the stack, and then stack would have to be put at the end of function B. You would have to restore the register from the stack, and so on and so forth. Okay? Any questions so far? Still not. So now who should save the register? As we said earlier, it could be saved by the caller. It could be saved by the callee. So the caller save behaves as follows. What the caller has to do is that the caller has to execute the registers to the stack, and then the caller calls jump and link register. And the callee has to do some stuff, and then at the end it jumps to the jump register back to the caller, and the caller would have to recover all the content in the stack. If you do the callee save, what the caller does is to call jump and link register, and then nothing. The caller doesn't do anything except calling the callee, and the callee does everything else. Okay? The callee has to rescue the registers from the stack, and then all the corresponding steps we discussed earlier. So let's have a look at your program. This program is called Stund to second. It takes an integer hour. It returns the integer multiplied with 3,600. Okay? And if we call this function Stund to second, now the question is that we also have the parameters we need to put. So the parameters we have, in this case, hour. We have two possibilities. One is to put that in a register and then give that to the function. Now, the question is that we have only sufficient amount of registers. Another method is to put the address. So one is called by value. Another is called by function. In a RISC-V convention, we can put up to 8 registers in arguments, and those are from x10 to x17. And the remaining, the additional ones you need would be put to stack. Okay, so let's keep in mind here. Now what do we have so far? x0 is 0, x1 is the return address, x2 is the stack pointer, and x5 to x7 are temporary registers, x8 are safe registers, x9 is a safe register, x10 to x11 are the function arguments and return values, x12 to x17 are function arguments, so 10 to 12 are the first two, 12 to 16 are the other remaining 6. x18 to x27 are safe registers, x28 to x31 are temporary registers. So everything seems to be explainable except some undefined terminologies called safe registers and temporary registers. So let me give you the definition first, and then we talk about how you use them. When a caller calls a function, the safe registers are supposed to be preserved across function calls. That means that when the caller caller A calls function B, the register 8, register 9, register 18 to register 27 are supposed not to be changed across function calls. The temporary registers are the registers that the caller cannot assure what the caller does, then it's not guaranteed to be preserved across function calls. Is that clear? If this is so clear, I think it's time to ask our questions. So is X0 caller safe or caller safe? Or not any of them?
If you just put an offset of 5, it jumps to the next instruction.
So
Because you actually have 12 bits to store your immediate, but just the least significant bit is ignored.
Yeah.
So the instruction basically gets a 5, but this bit is simply ignored.
But that means actually it's
So when you
10.
execute it, you make exactly a jump of 4. It's even encoded in the instruction, but not interpreted by the hardware.
Okay.
So you put the unshifted constant, but it's interpreted shifted, let's say. Strange behavior.
Are we able to talk about that concept in German today? I start to feel a bit
Free start now.
confused. I think the German part will be in next year, okay? So that we don't rush out. So as I said, stack is very important. That's the reason why I talk about this very, very slowly. And I'm pretty sure that you will be lost if you haven't done it before. It's a very, very strange concept. Your variable A is not your variable. It's everyone's variable. Your stack is not only your stack, it's everyone's stack. Okay, x0. x0 is supposed to be always 0, isn't it? So it's not any of them because it's always 0, so you don't need to do anything. So, good. So which of the following are caller safe? Which one must be safe by the caller? I'm too thirsty, so I don't want to drink this in front of camera.
Anyway, no one sees the camera picture at the moment.
Okay, it comes back to the very interesting question, right? So first one, if it's a caller safe, that means that the caller must have done it. Otherwise, the caller would have no chance. Right? So x1, we said it earlier. Oh, forgot to mention that you can choose this multiple times. So x1 is caller safe. because the caller has to save the address. Otherwise, after the caller calls callee, the x1 is already polluted. So x1 must be saved by the caller. There's no discussion on that. Okay, let's look at the others. Which one else must be stored by the caller? So the concept of being preserved across functions implies that the callee must make sure that lost preserved registers are always restored to its original value. So that means that if the caller, if the callee would like to use a register x8, in this case a safe register, then before the callee starts to operate on x8, the callee must make sure that this x8 is preserved across function calls. So it's the callee's job to preserve the safe registers. So see, everything with safe registers are preserved by the callee. And from the caller's perspective, it's very obvious that if the caller needs to make sure that after calling a function, the caller would like to use a temporary register, then that temporary register may have been already polluted by the callee. The caller has to store it in a caller safe. Okay? So anything that is not preserved across function calls must be stored by the caller. Is that clear? So you see that the temporary registers, the function arguments, must be stored by the caller. Okay? And the others, those are actually irrelevant to the context. The stack variables, the stack pointers, the global pointers, and 0, we already knew that. 0 is nothing to do with callee safe or caller safe. Okay? Any question on this? So if not, then let's go back to this call. How do we do the function call? I explained earlier that you can do the function call by value or by call by reference. So if you use C, it's called by value or call by pointer. In fact, call by reference. Call by value implies that the function is the argument you put to the function is a value. A scalable with a scalable scaled data type. For example, integers, characters, and so on and so forth. You can call a function by using call by reference. That means that the value you passed to the function is an address. That's a reference. By complex data structures, you would have to use call by reference. By primitive data types, you can do call by value. And of course, you can also do this by call by reference. And what is the difference here? So when you apply call by value, so let's understand what's the difference here. When you call a function by passing a value, how do you put a value to? You put a value to the argument. So you put this value, hour, to the register that represents the first argument, in this case, x10. And when you return from there, x10 is changed. So you basically only pass that with your stack value. So now the question is that if you need to pass something you want to change, and you will need to pass that through the reference so that you can change the content of that object directly. So you need to call by reference. Okay? So this is the main difference between call by value and call by reference. And let's have a look of this idea of swap. I want to implement this function swap. Swap means that we get index k, and we have an integer array. And what we do is that we basically swap the content in the element k and the element k plus 1. Okay, so now let's implement this in a context of assemblers. So first of all, we have to consider that this is a callee. So it would have to do some variable organizations. And it has to somehow execute the instructions, and at the end it has to restore the corresponding registers. Let's have a look of how we do it. So we are basically doing this. This is our body of execution. So we have this part as our body of execution. So what do we need? First, we take the corresponding address. The address, let's say x5, is our variable of, where is our x5? Okay, so x5 is our temporary variable. So it's a constant. We do the load immediate. x5 is 4. And then we overload x5 with x5 multiplied with x11. So x11, what is x11? Is the second argument. The second argument is integer k. So this is x11 is k. And what is x10? It's the address of our the array v. Okay? And then what we now do is that we take the base address x10 plus the offset of the array x5, and then we get these two together. We put the address to x5. This x5 becomes our address, the address of this array. The address of this element of the array we want to access. So this is basically the address of v of k. And now what we need to do is that we want to load the data from v of k, x5, and then put that data to x5 plus 4, and then load the data from x5 plus 4, and then put the data to x5. Well, we have to do it all at the same time, otherwise we cannot do swap. So that's what we do is that anyway, we don't need swap. We don't need the temporary variable anymore because we have the register. The register is directly our swap. Let's load these two elements directly to register. The value that is stored in v of k is loaded to x15. The value that's stored in v of k plus 1 is loaded to x16. And what we do is that we write x16 to the address k and the address of v of k, and then we write x15 to the address of x5 plus 4. Okay, so this is our program. Writing this program takes you probably some minutes of analysis. It will not be too complicated to do that. But the purpose of calling this swap function is to understand the context of swap. Okay, so what do we need to do? We first go back to analyze this program again. So we want to restore the registers. Let's forget about code safe or code safe. We want to somehow make sure that across function calls, everything is correct. Yeah? Let's first analyze how many variables we need to restore. So x5 is polluted. x15 is polluted. x16 is polluted. So that means that over here, we need to already put 3 variables to the stack. In addition, we would also put x1 to the stack before we call another function, right? Because we don't know what we are going to do, let's also store x1 before we do anything. In this case, we don't need to store x1, but if you want to call another function call over here, then you need to store x1. So you can start arbitrary things into the stack. In this case, we want to start 4 registers, x5, x15, x16, and then in addition, x1. So what should we do? This is a very important procedure. If you change the procedure, it's wrong. The first thing you need to do is to get the space. The second thing you do is to put the content to the space you have been granted. Okay, how do you make sure you get a space? Let's first move the stack pointer. We take the stack pointer, which is x2. x2 is set to x2 minus 16. We need 4 registers to be stored. Each one is 4 bytes. So we put 4 by 4, 16 address. So originally, we have this x2 pointed to this stack pointer. And now we take 1, 2, 3, 4 times 4 bytes to store 4 registers. Okay, so what we do is that we first add x2 with minus 16, and then put that back to x2. So we first get a space. This is what I meant. No matter how you want to touch with a stack, first get a space. And then the stack, when you get a space, you get a stack pointer. Move accordingly. And after that, let's write things to the space. So now after that, the space pointer is here. So we write here x5, and then x15, then x16, and then x1. Okay? Very good. So, now, at the end of this execution, at the end, so we have this prologue, and then we do whatever, call something. At the end, we have the epilogue, which cleans up the mess we have made over the time. So we start 4 registers to the stack. Now it's time to take them back at the end. How do we take them back? It's very important. Here, we first read the data from the stack one after another, and at the end we give back the address in the stack. Okay, let me do it again, because these 2 procedures are corresponding. First, at the moment when we need more space from the stack, we first grab some space from the stack, and then we write the content to the stack one after another. When we need to read the data from the stack back, we first read the content from the stack. And at the end of this rescue procedure, we give back our address. Okay? And if you don't follow this procedure, then you are at a high risk of having incorrect implementations. If you just look at this program, you say, come on, I can first write a nice 4 bytes here. Instead of putting this, I can first write x1 here. Can first write x1 and then x16, then x15, and then x5. So basically, this is x2. This is x2 plus 4. This is x2 plus 8. This is x2 plus 12. And x2 plus 16. And after that, I set x2 to x2 minus 16. Yes, it's correct from this logic perspective. But your program may be interrupted by the input and output devices, may be interrupted by other things. When you think that you are already writing your x1 to this address, if you did not move the stack pointer to the right address area earlier, then the other interrupt or the other service routine may consider this is the current stack pointer, and it would overwrite your x1. And then your x1 is gone. Okay? The operation of the stack is to make sure that no matter what happens, it's always correct. So before you write anything to the stack, you need to get a space. How do you get a space? You move the stack pointer correctly to the right address. After that, you start to write to the stack. How do you read from the stack? It's the counterpart. You first read the data from the stack, putting them back to the corresponding registers, and only after you have read all the data back to the registers, you can decrease your register. You can decrease your stack pointer to its correct address. Of course, if you want to do it slowly, you can increase and decrease the stack every time by 4 bytes. But no one does that. It's a waste of time. So you will do it in a batch. Okay? So that means, yeah. So now we have a question. What is the question about? What is the question about? I have no idea. Okay. Good. So now, so the question I want to ask is that, suppose that the stack pointer would be reduced by 128 bytes. So you want to reduce the stack pointer by 128 bytes. So you want to give up 128 bytes from the stack pointer. What is the maximum address offset that you can address from that register? Shouldn't we first explain that and ask this question?
It's explained.
It's already explained? Okay, so.
So when you have these push and pop operations, you do plus 4, minus 4, minus 4, minus 4. So people do that.
So let's say you are currently in the epilogue. You need to reduce your stack with 128 bytes. Okay? So we did is that we have this original address of the stack pointer, and we want to start to read in total 32 registers, 32 words. Okay? And with this excess of 32 words, what is the maximum address offset from the memory we should use? If we assume that we have 4 bytes registers, this is a very difficult question and very nasty, if I think about it. It would be 128. But you would think that 128 must be a wrong answer. Otherwise, I would not ask this question. 128 is definitely wrong. Is there 124? Sorry, is there 124 or 132? That's the only question. I think 32 is somehow too arbitrary. I would not take that.
It makes sense.
It makes sense? Why? Can you explain?
128 divided by 4.
What?
128 divided by 4.
128 divided by 4 would be 32. Okay, that also makes sense now. I think it doesn't make sense, to be honest. It only makes sense because you made it up. Okay. So, let's see whether we get a random guess. Ooh, so that's very correct. So, keep in mind that when we are doing this, we are in this epilogue phase. We access the address always with 4 bytes, right? When we start with 124, then we are going to access the word that is stored from 124 to the address 127. Basically, we are covering that range. Okay, 128 bytes. The last 4 bytes would be starting from 124 plus 3 and ended up with 127. Okay, so therefore it's very important. So we are going to give back 128 bytes in the question I just asked. So we would, before giving back that address, we load the first word to 1 something from this x2 plus 0. The first word 0 to 3. The second word 4 to 7. The third word 8 to 11, and so on and so forth. The maximum address we put would be 124 to load the word that is stored from 124 to 127. Okay, hope this is clear. And I think we are done of time for today. Next year, we would continue with the repetition in German, and then we will finalize this part by using the insertion sort. One more reminder that on Wednesday, there is a Weihnachtsvorlesung. The Weihnachtsvorlesung has 2 parts. The first part will be my test. The second part will be a quiz sequence. And I think you saw some strange stuff here floating around last week. So the winners may get some gifts. Will get some gifts. And I hope you will enjoy the Weihnachtsvorlesung. Weihnachtsvorlesung is not going to be graded, but of course, if you score well in the Weihnachtsvorlesung, then I think you will understand the context as well. This is not just a lecture that is completely irrelevant to the lecture. This Weihnachtsvorlesung would have very high percentage of assignments related to computer structures, Rechnerstrukturen Vorlesung, just with a favor of Christmas and Weihnachtsmann. See you on Wednesday.